the reason why I'm saying this out loud is because you want to focus on what the term is telling us. It's the marginal rate of technical substitution. So it's telling us the rate at which there is a substitution. And the technical part is letting us know that you're substituting between your inputs. So it's different from a finished good, where it's the marginal rate of substituting between two goods, MRS. The difference is here we're talking about the marginal rate of technical substitution. So then the question asks, what is the firm's expansion path? And when we had substituted our MRTS, and we had not substituted, but when we made that equal to the ratio of the prices of input, we found out that our expansion path, we would write it as K is equal to 4/9L. And that in general, or general form, if you will, I had K is equal to W/R times L. So this would be my expansion path. Then the next question says, find the combination of inputs that minimizes the cost of producing 2400. So since we knew that this is our expansion path, what we did was we substitute, this is the relationship between capital and labor. We substituted this in our production function to get labor as a function of quantity. And with labor as a function of quantity, we could substitute that in our cost equation. And from there, we were able to determine that labor capital combination. I'm sorry, when we substituted, I went a little bit ahead. When we substituted our expansion path into the production function, we were able to solve for labor that is being used to produce that level of output, and then use our expansion path to determine the level of capital. So we got our LK combination to be equal to 3616. Then this is where I jumped ahead when it says, what is the cost of producing 2400 units? Then we say our cost of producing 2400 units. In this case, since it asks for the cost of producing 2400 units, this is a specific quantity. So there is a specific minimum, there's only one minimum cost of producing 2400, and that minimum cost ended up being $288. And we found that by saying W times L, which is 36. So we found that by saying 4 times 36 plus 9 times 16, and that gave us the cost of $288. The question E is different from question D in the sense that question E is asking for the firm's short-run cost curve. And the short-run cost curve itself is a function, right? So whether your cost curve is a U-shaped cost curve, or whether it is just a straight line cost curve, or even if it is horizontal, so whether it is upward sloping or whether it's horizontal, one thing is for sure, that when we're talking about our cost curve, we're talking about an equation. Just as when we talk about our demand curve or our supply curve, we actually look at an equation to describe that curve. Now, your short-run cost curve is going to give us the relationship between the quantity and the cost of producing that particular level of quantity. So just as back again, when we look at demand curve, it gives us the relationship between the price of the good and the quantity demanded. When we look at the short-run cost curve, it is giving us the relationship between the minimum cost of producing a particular level of quantity and that particular level of quantity. Recognizing that everything that we've been doing here all the way down is to get to that cost minimizing outcome. So when we worked it out for this one, in this case, what we did, we recognized that the short run cost curve is actually coming from the short run cost equation. So just so that we understand the difference, this is your short run cost equation. And this cost equation is telling me that the cost is equal to WL plus RK. So, you know, as here, I use the cost equation to figure out the cost of producing 2,400 units. And that's because 2,400 units, I figured out the cost minimizing combination to produce 2,400 units is 36 and 16. Of course, there are other combinations that will produce 2,400 units, but those other combinations are not as cheap as, if you want us to use the word cheap, or are more expensive than using the combination 36 and 16 capital. But what if I think about, or what if I want to think about all levels of output, right? I don't want to be stuck on talking about only 2,400. If I care about 2,800, if I care about 2,000, all levels of output, what would be the equation that would help me to get to that number, just as how I got to the number of 288? And so what would be that short run cost curve? What would be that function? So if we use our short run cost equation, then instead of plugging in numbers for labor and capital, now we know that we have to plug in variables, and we also know that we need these variables in terms of quantity, if you will. If we look at this question, it says that and also to realize that it says that we're in the short run. So because we're in the short run, our capital is fixed. So with capital being fixed, and finding our labor as a function of labor as a function of quantity, right? Or labor as a function of quantity, let me look at my cheat sheet, what that ended up being. Labor as a function of quantity ended up being 3Q over 200, right? So basically what we did is that we substituted, we went to our production function and we wrote our production function as a function of labor. And even though we had the production function as a function of labor and capital, we could substitute for capital with that 16. And so that's how we got this L is equal to 30Q over 200. So with all of this, we get that our cost function as a function of quantity, looking at my cheat sheet, is equal to Q squared over 40,000 plus 144. In other words, I was able to substitute into my cost equation the labor function as well as 16. So here at K, I put in 16, and here at L, I put in 3Q over 200. And from that substitution, I was able to get my answer that, wait a minute, I think I made a mess. You guys are supposed to tell me the arrows as you see them. If you don't tell me the arrows, I'm going to imagine that, one, you're not here, or two, you're already sleeping, which is pretty weird because we just started. So actually, our labor function is q squared over, no, now you ask. That was a typo. So our labor function, L is equal to Q squared over 160,000. When we have L equal to Q squared over 160,000, then we can substitute that into the cost equation and then solve for our cost function. So that's how we get our answer. Okay. Okay. So now let's go to the finding out the firm's long run cost curve. Finding out the long run cost curve is similar to finding out the short run cost curve, meaning here we are going to use the long run cost equation. And our long run cost equation, no surprise, is the same as our short run cost equation, right? Our long run cost equation is the same as our short run cost equation. The only difference here is that when we were trying to find the short run cost curve, in the short run, capital is fixed at 16. Here in the long run, capital is equal to 4/9 of L. In other words, in the long run, capital, you can find your level of capital based on the expansion path. So in the long run, capital is equal to 4/9 over L, which is the expansion path. So we can substitute this into our cost equation, so substituting. We have C is equal to 4L plus 4/9K. No, sorry, 4L plus 9 times 4/9K. And this is equal to 8L. So now we have our cost function, or our cost equation, C is equal to 8L. So then you say, but what is L? In terms of quantity. So using the production function, we have Q is equal to 100 times 4/9L to the 0.5 times L to the 0.5, right? So in this case, so as I mentioned before, wherever you have K, you're going to plug in 4/9L, which is the expansion path. When we were doing the short run, we plugged in 16 for K over here, which is how we got the 144, and we plugged in 16 into the production function. So rather than plugging in a number in the long run, we're actually plugging in a function. And if you, and this would give us that our L is equal to 3Q over 200. That's where I got it from, or the first time. So you can substitute this into substituting into C. Then we will end up getting C is equal to 8 times 3Q over 200, right? So we get C, so this tells us that our C long run is equal to 3 over 25Q. So our long run cost function, this is what we have. This is our short run cost function from the previous situation. Now, there are a couple of things that I would want to say right here, just so that you guys, and I think I kind of said it with the previous presentation, but I'm going to reiterate it here, and I'm just going to go over it again right here, because there's a very important point that we don't want to miss, and that is, after finding the cost functions, whether it is in the short run or in the long run, we can always determine our average variable cost or average cost and or marginal cost from this information. So just as we did in the short run, so you could say in the short run, our short run cost curve in total is equal to Q squared over 40,000 plus 144. And I remember I did this, but I'm just going to do it again. Our three main measures in the short run that we care about is that our average variable cost is going to be equal to Q over 40,000. And our average total cost is going to be equal to Q over 40,000 plus 144 over Q. Our marginal cost, remember, that is the derivative of your cost function with respect to quantity. And the marginal cost is going to be equal to 2Q over 40,000, which is the same as saying Q over 20,000. So I'm going to write it just in case. 2Q over 40,000, which is the same as saying Q over 20,000. Now, for those of you who are adventurous and you like to imagine your graphs and you like to sketch graphs, given the information that you have, notice what is happening with our average variable cost function. As you start to produce a positive quantity, notice when Q is equal to 0, no surprise, your average variable cost is equal to 0. But when Q is equal to 1, average variable cost is, of course, 1 over 40,000. When it's equal to 2, it's 2 over 40,000. So one thing that you can see is that your average variable cost is increasing with quantity. For those of you who are adventurous, you love to go bungee jumping in the night over a very dark lake or over a very dark river that is raging. If you like to do such kind of adventurous activities, then if you take the derivative of your average variable cost with respect to quantity, you'll find that derivative is going to be positive, which tells us then that our average variable cost is increasing with quantity, right? The change in average variable cost when you change quantity is positive, it's increasing. When we look at our average total cost, however, our average total cost does something a little bit different. Our average total cost, you can then see that it has perhaps it is definitely greater than the average variable cost, but it has more of a U shape. For values less than 144, you can see that your average variable cost is, of course, it's increasing rapidly, but that increase kind of slowed down. In other words, it gets closer to the average variable. So you still have that increase, but it gets closer to your average variable cost as your quantity surpasses 144, because as the quantity gets larger and larger, let's say 200, this is 144 over 200, so you're adding a smaller amount. And if quantity was 1,000, this would be 144 over 1,000, so you're adding an even smaller amount. You can see it's getting smaller. So it has that kind of a weird shape going on. And you can always try to find out the minimum value, where it reaches minimum or something, but it's always increasing as you see, but you get my point. Then your marginal cost, if you want to graph your marginal cost, it behaves similar to your average variable cost. But one thing you should notice, very interestingly, is that your marginal cost is always greater than your average variable cost. And that's no surprise, because in the sense that my average variable cost is always increasing here. So it's no surprise that my marginal cost is greater than my average variable cost. All right, so then with the long run, let me see if I have enough space. Yes, I do. So with our long run cost function, we had, wait, let me make sure I'm following through. In the long run. So in the long run, we have our CLR is equal to 3 over 25 times Q. And by the way, 3 over 25 is the same as 0.12. So either one, whichever one you're comfortable with, that is fine. In the long run, we do not have any fixed costs. So it turns out your average variable cost is really your average total cost. And sometimes you'll see some textbooks or somewhere writing it, calling it your average cost. And all of these are going to be equal to 3 over 25 or 0.12. So these are constant, and that's a horizontal line. Essentially, this is what it looks like. This is your quantity. This is your average cost. At this value, 0.12, and this is a dollar amount. So it costs this firm 12 cents on average in the long run to produce the good that it is producing. Also, the marginal cost is equal to 3 over 25 as well. Remember, your marginal cost is equal to the derivative of your average cost function. So your marginal cost is also constant at $3, 3 over 25, which is 0.12. So I want to make 2 quick points right here. One quick point well, let me make one now. Later on, I'll make it. The other one I'll make when I'm in chapter 8. The quick point I want to make here is to notice that when your average cost is constant in the long run, or when your average total cost is constant, right? In such a situation, basically what it's saying is the amount it's costing me to produce the good on average is the same. Now that is not too far-fetched to think about. If I'm producing 100 units and it's costing me on average to produce 100 units $2, then it means that my total cost is $200, right? If I'm producing 300 units and if I'm producing 400 units and my total cost is $800, then I'm also getting an average cost of $2. So the cost per unit is the same. Then what that is also telling me is that as I increase or produce an additional unit, the amount that I'm adding, right, the marginal cost, the additional cost is going to be the same. So whenever your average cost curve is horizontal, or whenever it is constant, the marginal cost is equal to the average total cost. And by the way, in the short run, whenever your average variable cost is constant, your marginal cost is going to be equal to the average variable cost. When we get into chapter 8, we're going to talk a little bit more, explore a little bit more this fantastic relationship between marginal cost and average total cost and average variable cost. No surprise, they're related. They're like cousins. If you think about them, their last names are the same, cost, but their first names are different. One is called marginal and the other one is called average. Okay, so now we have all that is going on here, and if we wanted to, we could always sketch a graph to represent everything that we have calculated so far. And I'm going to go up to here simply because I have space, and I am going to try and sketch this graph right here. So basically what we're seeing is that this is our labor, this is our capital, this is my iso cost curve, this is my iso, it's tangent, believe it or not. This is my iso quant. The value here is Q is equal to 2400, right? This point is 16 and this point is 36. So that's what we just figured out in terms of finding everything that we're doing here. So this firm is in equilibrium, right? It's in a production equilibrium, if you will, if we can borrow that term. And that they are producing 2,400 units, whether it's per week or per month or per day. They're producing 2,400 units using 16 units of capital and 36 units of labor. And they're doing this at a minimum cost of $288. So now we're told that there is a shock to our system and or to this firm's equilibrium, and we're told that suddenly demand conditions improved and the firm decides to produce an additional amount. Notice the external shock that I have used in this market, right? Now, I could have always talked about a change in the price of the inputs, which is also an external shock, but just to make things nice and easy for us to grasp what is happening, the idea is the firm is in its long run and it is currently producing 2,400 units and it is happy. It is happy as can be. But then all of a sudden, unbeknownst to the firm, which is why it's suddenly, unbeknownst to the firm, demand conditions change. Because remember, the firm only care about supply and supply conditions in this kind of situation. So demand conditions change. He doesn't know about this. But then when he realized that consumers are probably buying more, maybe that was the change, their income went up and they're buying more or something like that, or all of a sudden a report comes out that says that this product, whatever it is beneficial to their health. Like if they came out all of a sudden and say, you know what, if you eat one tub, the individual tub of cottage cheese every day, you live longer. Or if they say you eat that cottage cheese every day, whatever internal illnesses, whatever internal intestinal illnesses you may have, whether you have Crohn's disease or whatever else that is going on with your intestines, if you have one tub of cottage cheese every day, you will not only cure and get rid of this disease, but you will ward it off from happening to you. Imagine such a breakthrough with science just came out like that. Then in such a situation, you can see how consumers, their tastes and preferences will be motivated towards purchasing cottage cheese and eating more cottage cheese than they have been eating. They probably don't even need the syrup and the fruit on it to make it flavorful. They will just eat the pure, original, untouched and unmessed with cottage cheese. So such a thing you can imagine will happen. Demand conditions change, and now consumers are purchasing more of a good. So because of that, and because they recognize a higher demand, the firm decides to produce 4,800 units. So the question is, what is the firm's cost minimizing combination of inputs to produce 4,800 units? Very importantly, in the short run. This is very important because here we have a shock to the firm and its production process, and the firm will have to go through a short run change and a long run change, right? So if all of a sudden it's going to produce more output, yeah, you may be able to change your variable input, hire more workers, etc., get more materials. Maybe your more materials is milk or whatever else it is you use to make that cottage cheese. They have to get more of the inputs, the variable inputs, and that would be easy for them to do in the short run. But when it comes to increasing their capacity, right? Maybe they need an additional machine. Maybe they need an additional location to take on producing 4,800. When it comes to such a situation, then the firm actually has to now think about that as a long run change. So the short run change is that they can only change their variable input. So now, if we want to know what is a cost minimizing combination, well, what are you producing? So you use your production function. So using the production function. So in other words, you're using Q is equal to 100 L to the 0.5 and K to the 0.5. So if this is 4,800, this is 100 L to the 0.5. My K, I know, is 16 in the short run to the 0.5. So this ends up being 400 L to the 0.5. Right? So L to the 0.5 is going to be equal to 4,800 divided by 400, which is, of course, equal to, that's just way too much math for me. If you guys let me figure this out from my rickety calculator before you, that's just that. L to the 0.5 is equal to 12. Okay, thank you. Someone got it. And yes, thank you for putting up the answer for my next question. So if L to 0.5 is equal to 12, then this implies that L, labor, is equal to 144. Fantastic. So the first cost minimizing combination of inputs will now be 144, and now he's still using his 16. What does this look like on a graph? Let's just make sure we're all together. So I'm going to try to do this with a steady hand. Now, try to be as accurate as possible, but not the greatest. So the point does move along the curve, but which curve? Because remember, for this curve that we have, so that's a good point that you're raising right there. This is for 2400, but because we now want 4800, right? Because we now want 4800, we have to have an isoquant that is to the right of the original isoquant. And so this point, if this is our k that is equal to 16, then what the firm does is move to this point where it's using 144 units of labor, moving up from using 36 units of labor. So you started out at point A, you move along the line, you move along to point B to get to the new quantity, the new isoquant. But we know that this is not cost minimizing. How do I know this is not cost minimizing? Not because I have a crystal ball or an 8 ball and I look in it or I ask, is it cost minimizing? No. What? I look on what we have been doing. We have established that point A is a cost minimizing point that was determined using the slope of the isocost and the isoquant. My point being, if I go to Q equals 4800, then this slope, that the slope of the isocost and the isoquant would not be equal at point B. But let's say that geometry was not one of our strongest points all the way back in pre-K when they had us put in shapes into shapes. Maybe we were trying to force the circle, the cylinder into the star. You know, maybe geometry was just not our forte. Well, another thing that we can look at, is our expansion path. The expansion path tells us the labor capital combination that will allow us to minimize the cost of producing any level of output. As long as the relationship between labor and capital is 4/9, then I'll be able to produce any level of, that combination would be a cost minimizing combination to produce a particular level of output, a specific one. So in this case, if I'm using 144 units of labor, then if I plug in 144 into, so I'm going to make this my aside right here. This is, you know, sometimes when you go to the restaurant, the all-you-can-eat restaurant, or even if you go to a regular paying restaurant, you know, a la carte, and you purchase something, and you want to get that chocolate cake, and you want to have it there so you can see it and remember it. So this is what we're putting right now up on the slide. We're going to put up a slice of chocolate cake that we're going to go back to eating that chocolate cake in a few minutes, but we want to make sure that we have it, that we see that it exists, and it's something that we're going to eat in a few minutes. And if you guys really do not like chocolate cake, which is possible, right? Understandable, I don't know, but it is possible that you don't like it, then think about something that you like. Think about, I don't know, think about an icicle. Everyone likes icicle. They have icicles out there in the summer. So think about an icicle. So this is it on the aside. If labor is equal to 144, then using, or I should just say then using K equal to, so if I take 144 times 4 divided by 9, I get 64. Then K equals 64 would be the complementary, would be the capital, which leads to cost minimizing. Cost minimizing combo to produce Q equal to produce Q equal 4800. So if I'm already using 100, so let me just repeat what I said, just in case you guys got completely lost in my joke. I'm trying to give a joke here. I try to give as many jokes as possible just so that this is not too boring. But you know, sometimes it feels like it falls flat because I can't see you, so I don't know if you're laughing. And then I don't even see a thumbs up. I mean, you know, sometimes, you know, you can just let me know you're here. Thumbs up, or, you know, or even a thumbs down, even if you don't like my jokes. Thank you. Thank you so much. I got an appreciation. I appreciate the appreciation. Okay, so and thank you. I got a thumbs up. I appreciate that too. So okay. So let me say what I said again, just to make sure we're all together. Just to make sure that we're all following. Good. Okay, so this is what I'm saying. So if we look, we know that the cost minimizing combination using the expansion path will always be LK, where the relationship between L and K is 4/9. So when we do that, it's on reactions. So if you look for reactions, you'll get it. So when we do that, when we have K is equal to 4/9 L, then if I'm using, as in this case, 36 units of labor, then my capital will be 16 units of capital, and I know that that combination is cost minimizing. Okay, fine. So now we have the shock, and with the shock, I am increasing my labor and I'm not doing anything to my capital. So what I was trying to say all along is that beside just knowing intuitively that I have now messed up this relationship between capital and labor, because if I'm saying capital should be equal to 4/9 of labor, and I went ahead and increased labor, but I didn't do anything to capital, then I now know I've messed it up. But beside that, the point that I was trying to make right here is that if we stare at this graph, the first thing is, if you try to use an isocost that is parallel to the one that we already have and try to find that point of tangency, it will not occur at point B. And so if that point of tangency is not occurring at point B, then point B is not cost minimizing to produce 4,800. But then and so this is where I went off on my little tangent. I was saying, but what if we cannot visualize and we don't like graphs and we can't really see what I'm talking about? Well, here's a little way that you could figure it out. So this is back to, what if I'm in the real world and I'm trying to find that combination of labor capital, and somehow in the long run, I now know the units of capital that I'm using and the units of labor. And so I can create my own expansion path if I wanted to. Then what I'm saying here is, if you plug in your 144 for labor into that expansion path equation, then you're going to realize that your capital is going to be different. And in this case, notice that your capital ends up being 64. So this also would tell me that this combination, 144/16, is not a cost minimizing combination. So that's just one thing that I wanted to say right there, that this combination is not a cost minimizing combination. If I'm using 144 labor, the cost minimizing combination with 144 labor would be 64 capital. Now, for those of you who are adventurous, you would also realize that using 144 labor and 64 units of capital is going to give me an even greater amount of quantity. It's going to give me something that's greater than 4,800, which is not what I want anyway. So that's just my aside. So then it comes to the next question. So, but anyway, so here in the short run, so after the shock and after consumers are now buying up the cottage cheese just because, you know, they hear that it will cure whatever intestinal disease you have or prevent one from occurring, then this firm in the short run decides to hire more workers and speed up on its production in the short run to do 144/16. So the next question says, what is the short run total cost and short run average cost of producing 4,800? Well, we can figure that out quite easily. First, we can use the equation cost is equal to WL plus RK. We can use that, or we can do something even more funner. We can do something even more fun and use the cost equation that we have derived from in part, I think it was part D. No, part E. Use the cost equations derived in part E. So we can say using. Then we have our short run cost function. We found that out to be Q squared over 40,000 plus 144. So since we're talking about 4,800, my short run is equal to 4,800 squared over 40,000 plus 144. And you see, by now, I thought someone would have thrown up into the chat real quick before his or her colleagues what the answer is. Because you know I'm going to ask you, and I'm going to say, don't allow me to use my rickety calculator, my adding machine, and I got it. So it is equal to $720, right? Using my adding machine, I did this before you guys. You guys are like, you guys are a good 70 years. No, I used my calculator. It wasn't a cheat sheet. And you guys are a good 70 years younger than me. I'm able to use my calculator and get to that answer. Then we want to find also, it says, what is the short run total cost and the short run average cost of producing 4,800? So the average total cost, which is the same as the average cost, is going to be equal to our short run cost divided by quantity. So it's going to be equal to 720 divided by 4,800. Let me see, did anyone put it in the chat? No. So I have to do it on my calculator. And I got 15 cents. Wait, let me see, someone put it in the chat before I wrote it up. Thank you so much. And yes, you're correct. You put it in the chat before I wrote it up. Bonus points for you. So the average total cost is 15 cents, and so 15 cents per unit to produce in the short run. Now, for you guys on the side, you can see that you would still get the same. You'll still get the same information if you had actually said that the short run cost is equal to WL plus RK, and if you had said 4 times 144 plus 9 times 16, you should still also get 720. You'd still get 720. So it doesn't matter which one you're using. I just feel like we should use the cost function since we figured it out. Okay, real quick. What is the firm's cost minimizing combination of inputs to produce the 4,800? Now we're getting to the meat of the matter, because now we want to find out that cost minimizing combination of inputs to produce that 4,800. So we would do it in the same. Since I'm talking about cost minimization, I'm going to use my expansion path along with the production function. So I'm going to say 4,800 is going to be equal to 100, 4 over 9, L all to the 0.5 times L to the 0.5. So my 4,800 is equal to 200 over 3 times L. My L is equal to 4,800 in my rickety calculator times 3 divided by 200. L is equal to 72. Very good. Exactly. And tell me really quickly, what is my K? Yes, so it is 32. My K is equal to 32. So my combination is now 7232. Very good. Exactly. So you guys got it. So one of the things that I want you to notice is that to find that combination, now that I'm in the long run, notice that I'm going to find that labor capital combination, once again, that follows with the expansion path. So because of that, I'm going to realize in the long run that I do not need to, you know what, I'm going to come right to that point just in a minute. I am going to find that labor capital combination that will agree with that relationship or be a point on my expansion path. So in reality, what I'm finding out is I don't need to hire 144 workers. And maybe these would have been temporary workers that I hired. As I hired these temporary workers, while I try to figure out what it is, which combination that is really optimal for me, and get to the point of having that combination of 72 labor and 32 capital. So, you know, the point that came out into just now in the chat, so it says, since my output is twice that of my input, no, since the output is twice, is it that I'm doing twice for the input? And as it turns out, yes. That is a very, very good point to make, because what is happening is that if you look at, so the answer is yes. If you look at your production function, and if you add the exponents 0.5 and 0.5, you get 1. So that means if I'm using twice as much of input, I'm going to get twice as much output. So I really do have that constant returns, very good. I really do have that constant returns to scale going on. Okay, so so if I look here, this point with 72, 32, it's going to end up somewhere, let's say here. And this is going to be my point C. This is 32, and this is 72. And with my numbers, they actually so happen to be those same endpoints. So I'm going to end up there. So I move from A to B, and then I move along my my isochron to point C. You can double, okay, so to go to the question, is there any case where you double the inputs and do not get the expected outcome? So if you double the inputs, there's one out of three things that's going to happen. Either you're going to double your output, or you're going to more than double your output, in which case it's an increasing return to scale, or you're going to less than double your output, which in that case is a decreasing return to the scale. One way that you can think, I'm trying to think about how you can actually get the decreasing returns tend to be a little bit hard. Increasing returns tend to be a little bit easier if you think about things like technology, etc. You can imagine increasing returns to scale in that case. You know, just think about you know, I don't know, broadband or something like that, something that, you know, or some kind of information technology that, you know, once other people get onto it, you'll get that increasing returns to scale. The decreasing returns to scale, however, would come in the I can't think of one right now. But if I think of it, then I'll definitely share you. Maybe when I get into the firm, then I get farming. So that's the funny thing that you said farming, because I did think about farming, but it's just that the land is fixed. I did think about it and I was thinking about cows, because, you know, to keep with that whole theme, cottage cheese, cows, dairy. I was thinking that if I had more cows, that if I double the amount of cows that I have, but if I don't have enough grass or food or whatever else it is to feed them, or land space for them to roam about, I probably would not be able to double my output. So that's why I was kind of hesitant with cows. The only other thing I can think about is baking. If you try to bake a cake, or maybe you don't bake, that's okay. Don't worry about it. There's no judgment here. Maybe you've made pancakes. And maybe if you look on the pancake box, on the back of it, it tells you how many cups to use, or you know, back to baking a cake. You know, if you use 1 egg into your mix, you know, you're getting a certain output. If you use 2 eggs, chances are you're going to get more than double the output in your cake or in your pancakes, or whatever it is that you're making, you're baking. I'm just thinking about baking or cooking. Or, you know, sometimes when they give you a recipe for a dish, when you go to one of those, and you get a recipe for a dish that you want to make for 4 people, and they give you a certain number of ingredients to use, and maybe they say a pinch of salt. And then when it goes to making for 8 people, they don't say 2 pinches of salt. You know what I mean? Like, they would probably say less than, they'd still say a pinch of salt, or maybe just a little, you know, just a toss, which is somewhere between 1 pinch and 2 pinches of salt. But you get my idea. So you're going to get it's going to give you some outcome. The question is the outcome going to be this double, less than double, or more than double the outcome? Okay, fantastic. So right. So here we get into, like I was just, you know, to finish up, fantastic. Just to finish up with that point, here, basically in the short run, you're here at point B, but you know it's not cost minimizing, because if you try to figure out, I mean, I can put it on my rickety calculator right here. 144 times 4 is 576, and 64 times 9 is 576 as well. So 576 plus 576 on a good sunny day is 1,152. So at point B, I'm using $1,152 to produce 4,800 units of output. And that is not cost minimizing, because now we're going to find out that to produce point C, I'm going to be doing this at a lower cost. It's not going to be 1,156, and it better not be 1,152, right? So 72 times 4 for my labor is 288, and 32 times 9 is 288, and 288 plus 288 on a fantastic day is equal to 576. So I can produce this 4,800 at a cost less than what point B is accumulating for me. So I know it's not cost minimizing. So there are many ways that you could tell it's not cost minimizing. It's not 1,156, it's 720. That's what we said from long ago. 720. 720 if we're using a combination of 144 and 96. The total cost is 720. Alrighty then. So now that we have this cost minimizing combination, the last part says, what is the firm's long run total cost and average total cost of producing 4,800? And we are just going to use our cost functions for this. So if you remember, your CLR is equal to 3/25 times Q of 4,800. I don't think you guys should trust my calculator. I really think you should put the answer up in the chat. And my average total cost, thank you. That's what my calculator gave me. And my average total cost, do I need to calculate this? Y'all, I don't need to calculate this because we found out from question F, we found out that it is constant at 12 cents. So you could do your 576 divided by 4,800 just to make yourself happy. But you should realize that from our previous working out of the average total cost using the function, we found out that the average total cost is constant at 12 cents. All right, so this is the end of that classwork, lecture activity 4. And I will still even post the answer key. I know that some of us like to go over what was being done. So the answer key will be posted that you can see. But at this time,